Welcome back to the Institute. In this lecture, we are basically going to understand the concept behind reducible and irreducible polynomials. Okay, so let's say that you have a polynomial, okay? A polynomial, let's say a function f of x, okay? And this function here, this particular function f of x is being done over a particular ring, right? Over a ring like ZP, Z, or Q. You know all these things, right? This is a rational, this is integer, and this is integer and a prime. Now, those polynomials in this particular ring will be either reducible or irreducible depending on how it works, right? So if the polynomial cannot be factored as a product of two non-constant polynomials in that particular ring, then we term it as irreducible polynomial. Are we good with that? So if it cannot be factored as a product of two non-constant polynomials in that particular ring, then we term it as irreducible polynomial. Now, if it go the other way around, right, then we term it as reducible polynomial. So in that instance, it can be factored as a product of two lower degree polynomials in that particular ring. Okay, so that is the basic definition to these two concepts. Now, give me some short minutes. I'll be right back with a question so that we understand the concept very well. Okay, I'll be right back. Welcome back from the short break. I believe you have been able to reflect on the concepts and you're okay with the definitions. Okay, now let's look at this particular problem, right? This is our problem 1. We want to indicate whether each statement is always true or sometimes false, and then we'll justify it, right? So the first problem is every polynomial of degree 1, okay, that is f of x is equal to as plus b, is irreducible, okay? And b, x squared plus 1 is irreducible in real under polynomials, right? But reducible in complex under polynomials. X squared plus 1 is equal to x minus I times x plus what? I. Right. This is an interesting problem and I really love it. So first of all, this particular question, once you see this, the first question you have to ask yourself is that what do you need? Okay, what do you need, or what is a linear polynomial, right? What is a linear polynomial? Because that is the A part, right? They are saying that every polynomial of degree 1, f of x, as plus b is what? Irreducible. And this is what? A linear polynomial, right? As plus b is what? A linear polynomial. Now, what is a linear polynomial? We know that a polynomial is of this form, right? A naught plus a 2 x squared, right? Plus up to whatever it is. But linear is ax plus b, right? Where a here is never equal to what? 0. Because once a is 0, you are no more having what? A linear polynomial. It will tend to a constant polynomial. So a should not be what? 0, so that you can have a linear polynomial. I believe that is good. Okay, so once we know that, you know what a linear polynomial is, now the next question you have to ask yourself is that, can you factor a linear polynomial? Right? Can you factor a linear polynomial into two non-constant factors? Right? Can you factor a linear polynomial into two non-constant factors? The answer is a big no. Why? You have ax plus b, right? The only way you can write ax plus b is either writing it as 1 into ax plus b, or saying that you have ax, ax plus x plus b over what? A, all multiplied by what? A, right? The only way you can write this expression is either writing 1 into the expression, or A into this expression. You know, when you expand this, you're going to have AS here. When you bring this here, you're going to have what? This cancel the A, and then you have your B. So the only way you can express this expression is this or this. So you cannot factor a linear polynomial into two non-constant polynomials. So that question has been answered. So it's a big no. You can never factor a linear polynomial in any way. Okay? So that is the justification. So the first justification we did was, what is a polynomial? So that is 1. And then the second part was, can you factor it? And the answer was what? No. Right? So we've done the justification. Now we've understood the concept of what? Linear polynomial, right? So we can conclude that, therefore, every linear polynomial cannot be factored, or cannot be factored, right? So it is considered to be what? Irreducible. Okay, so now let me give you the reason. Okay, I've given you an overview definition of what the reason why you cannot factor it, right? So now the reason is, so yes, this particular statement is irreducible, right? So the first thing you have to say is that, yes. So the question A, you have to write that yes, always true. This is always true. Then you come down and come and justify or give a reason to this, right? So now the reason is that any degree that is 1, okay? Any degree that is 1 polynomial, any degree that is 1 polynomial, right? As plus b over a field is irreducible. This is because it cannot be factored. It cannot be factored as a product of two non-constant polynomials of lower degree. Right? So that is the justification to the question, the A, 1A. Now, I believe you are good with the A. So put it in your mind that every linear polynomial, right? Every linear polynomial of degree 1 is irreducible, and that is perfectly yes. So it is yes, always true. So this is the justification. It cannot be factored. Now, the B part says that x squared plus 1 is irreducible in real under polynomials, but reducible in complex under polynomial. And the expression is x squared plus 1 is equal to what? X minus I times x plus what? I. Now, we all know that real numbers contains everything, right? But I believe that complex numbers should supersede this, but they say that this supersedes this. So we will take it like that. You know, complex numbers contains all real numbers, and they consist of complex numbers as well, which is the I, right? So for instance, we have square root of -1. It's a complex number and it is here, right? Now, the reason we can give over here is that you see x squared plus 1 is irreducible in this, but it is what? It is possible. It can be what? Reducible in the complex numbers, right? So we say that their statement is right, absolutely right. Okay, so B, the statement is absolutely right. Okay, so x squared plus 1 is irreducible. X squared plus 1 is irreducible in reals under the polynomials, but reducible in complex under the polynomials, right? So now our reason is that when you take this expression, right, over a real number, right, real number under a polynomial, you can say that the discriminant, right, the discriminant is less than 0. Okay, the discriminant is less than 0. So let's say that you are saying -4, it is less than 0. Okay, now this expression right here, this discriminant has no real root. Okay, so that's this expression has no real roots. Okay? But when you come to the complex, even this will have a real root. Okay? This one will have a real root. So when you come to complex, right? When you come to complex, x squared plus 1 equals x minus 1, x minus I, s plus I is reducible, right? Is reducible. So the statement is valid, always true. The statement is always true. So that is basically the basic justification you can give to this particular problem. I believe it was interesting, right? Now let's look at some other problems that is related to irreducible and reducible issues. Okay, give me some short minutes. I'll be right back. Welcome back from the short break. I believe you have been able to reflect on that particular problem and you're good with it. All right, so now question 2 is, this is question 2, right? Consider the polynomial f of x equals x cubed minus 3x plus 2, right? Now, this is the polynomial, okay? And the question A is, we want to determine whether f of x is what? Irreducible over the field of rational numbers. Now, once we are done with this, we want to see, right? B says that if f of x is reducible, then we should factorize it into irreducible polynomial over Q. You are aware that Q is what? Rationals, right? So now, how are you going to tackle this? How are you going to determine whether f is what? F of x is what? Irreducible over the field of rational numbers. So first of all, what we can do to do this particular problem is that we have to check if f of x is irreducible over Q. Okay, so first step, step 1, we have to check if f of x is irreducible over what? The rational, which is Q, right? Now, what we are going to do in there is we are going to use trials, right? You know, before you can determine one factor, you have to do trials. So you put in, let's say, 1 here and see if the result will give you 0. Are we good with that? So let's say that you put 1 here, you have 1 minus 3 into 1, which is 1 minus 3, negative 2, right? Negative 2 plus 2 is what? 0. Interesting. So that means x is a factor to this particular expression. Great. So we are going to say that x, when we substituted x equals 1, this expression was able to give us what? 0, which shows that it's a factor. right? So x equals 1 is a factor. So it means that x minus 1 is a factor. Now, we are going to use this factor to find the other factors, right? So we are going to use either the synthetic approach here or the long division approach. So we are going to take this and then pick this. So we are going to say that x minus 1, I'm interested in the long division approach. You can use the synthetic at your end, right? So the long division approach, you know what to do. Put your divisor here, and this is your what? Your function. So x cubed minus 3x plus 2, right? So this comes here. So x cubed divided by x, you get what? S squared. You write it boldly, right? Now, once you have it there, use this thing to multiply everything in the brackets. So first, this multiplies this, and you have what? S cubed. This multiply this, and you have what? Minus s squared. Now, we don't have anything for this section, right? So make sure you put 0 there so that you don't become confused. Now, subtract them. Okay, so this minus this, you have 0. This minus this, you have what? Minus 3x, right? Can you see something? So we can see that we don't have any term for s squared here, right? So it means that s squared here is what? 0s squared, right? So 0s squared minus s squared becomes plus s squared. So we have plus s squared. Then minus 3x minus 0 becomes minus 3x. Then you have your plus 2. Right? Now, this is what we have. So it means we have to come down again. So this divides this plus x. Right? Now, this will come here. You have s squared. This comes here. You have minus x. Is that good? So this here, remember to bring your 0. So this, subtract this, you get 0. Minus 3x minus x becomes minus 2x plus your 2. Great. Now this here, minus 2x divides x. So this takes this, and you have minus 2 in here. Good. So this is what you are going to do. This is the last element. Multiply everything. You have minus 2x, this plus 2. Subtract. This, you get 0. This, you get what? 0. So it's truly that x minus 1 is a factor to this particular polynomial. So now our expression becomes x minus 1 times s squared plus x minus 2. Right? And this right here, if you factorize this, okay, if you factorize this, you're going to have x, you're going to have x plus 1 and x plus 2, right? If you factorize this, you're going to have s plus 1 and s plus 2. So once we have this, then this expression can be factorized again, right? But this, now we are not going to use long division again. We know that this is a quadratic expression, okay? So we have x minus 1, and then this, when you factorize it, you are going to have x plus 2 and x minus 1. In here, we are seeing some interesting items here, right? This and this, they are the same. So it means that you're going to have x minus 1 or squared. Great. Then you have x plus 2. That is so beautiful, right? So that is the answer to the question. That is the answer to the question A. That is the answer to the question A. Now, what we are going to do for the B is that, okay, let's try to conclude for the A first. So f of x equals this expression, f of x equals x minus 1 all squared, x plus 2 is, so it is what? Reducible. Okay, it is reducible. And that is factorization over Q. That is rationals. Okay, that is factorization over rationals. Now the B part, to do the A part, I want to give you some small assignments, right? So look at the trend. Look at how we did this. Now they are saying that if f of x is what? Reducible factorize, it's reducible, we should factorize it as what? Irreducible polynomial over what? Q, which is what? A rational. So I want you to do that for me. So this is basically the solution. Okay, this part is not going to be anything difficult. All right, so please leave your answer at the comment section if you get it done. Welcome back from the short break. In this particular problem, we want to determine all maximal ideals of R. You know, R is a ring, okay? R equals Z12. You know, 12 here is integer modulo 12, right? So integer modulo 12 be the rank of integers modulo 12. R equals this, be the integers of what? Modulo 12. Now I want to determine all maximal ideals of the ring. So you know that in integer modulo 12, the ideals correspond to the divisors, right? It corresponds to the divisors of what? 12. Okay, so once we know that, then we have to know that the maximal ideals also corresponds to what? Let's say D, right? So the maximal ideal corresponds to what? A D. This, if you see this symbol, it's an ideal. Anywhere you see this symbol, it's an ideal. So if you see 2, 2, this is an ideal. All right. So this is an ideal in here. Okay. Now, that D is an ideal, is a maximal ideal such that the Z12, the modulo 12, is a field. This is a maximal ideal such that Z12 right is a field, right? So once you know this understanding, then you are good to go. So now let's try to check this before we can determine all the maximal ideal of the ring. So what we have to check is, in the modulo 12, we have 3, we have ideal 3, we have ideal 4, we have ideal 6, right? So with ideal 3, okay, with ideal 3, this right here implies that you have Z12 ideal 3, right? And this right here is equal to Z4, right? This right here, this is just like modulo, right? So, this will go here what? 4 times. And for modulo 4, okay, modulo 4 is not a maximal ideal. It's not a field, right? This is not a field because this right here is not a prime. Because this thing is not a prime, this thing does not qualify to become what? A field. That is the whole idea. So this is not a field because this here is not a prime. Now we have to go to 4, right? So let's take 4. So if you take 4, then it means that this implies that Z12 4 will be equal to Z3. This will go here 3 times, right? So, and we are very much aware that 3 is a prime number, right? So this qualifies this to be part of what? The field, right? Once it is a field, it is a maximal. Once it is a field, it is a maximal. So now we have 1. Now let's check the 6, right? Let's check the 6, okay? So the 6 means that you have modulo 12, 6, and this right here goes into 12 2 times. So you have Z2. And this, one of the interesting aspects of this thing is that the only even integer, right? The only even number that qualifies to be part of this is what? 2, because 2 is a prime. The only even number that is part of the prime numbers is 2, right? The only even number that is part of the prime numbers is what? 2. That is an opportunity, right? So this is a field. This is also a field. And since this is a field, it becomes a maximal ideal. A maximal ideal. So in all, we can say that the Z12 is the only one that is not a field. And since it is not a field, it is not a maximal idle, right? It is not a maximal idle. So the only maximal idle we have here is this and this. And their corresponding idles are 4 and 6, right? So the maximal idles of R, the maximal idles of R will be equal to this and this. That is beautiful, right? So that is the process you have to go through to be able to determine your maximal idle given a problem of this nature. So first of all, you have to check the element here. It has to be a prime number. And you know prime numbers, right? It has to be a prime number. Once it is a prime number, then it qualifies to be a field. And if it is a field, then it is what? Straightforward. It is a maximal idle. And that is it. All right. Thank you very much for watching. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'm going to give you more updates. Bye-bye. Thank you very much for watching. I really appreciate your time. Until the next video, keep learning and stay inspired. Bye-bye.